Hi everyone, my name's Tom and I'm one of the instructors for Math 1109. So this is just a recorded review session of the sample midterm, or sorry, the sample final exam. So I'm just going to go over it question by question. And if you're interested in an in-person review session, the other instructor, Ryan Jabara, is doing one on December 11th at 6 p.m. And that's going to be in the RBC lecture hall in the CE building. But yeah, this is the recorded one. So yeah, so let's get into it. So the first question is a veterinarian seeks to study the relationship between the length of a dog's canine teeth in adulthood and the number of months it took the dog to reach adulthood. She measures the length of the dog's canine teeth for 32 adult dogs and asks their owners how many months it took the dog to reach adulthood. Okay, so part A, what's the population of interest? So she's interested in all dogs. What's the main research question? So that's kind of right in the question. That's right at the in the first sentence. Is there a relationship between uh, length of dogs' teeth in adulthood and the number of months it takes to reach adulthood? Okay, so that's the main research question. What are the units? So there we want to think about what's being sampled. So here the units are adult dogs. So that's what um, the experimenter is taking samples of. D, what's the size of the sample? So that's pretty easy. It says that right in the question. It's 32. E, is this observational or designed? So this one's observational. So the experimenter or the researcher isn't interfering with the units. She's not controlling them or assigning different units to different treatments or doing anything like that. Merely taking the units and observing or measuring, in this case, the tooth length. So that's why it's observational. F, what are the variables in the study? So there are two variables. One is the length of the adult dog's teeth, and the other variable is how many months it took to reach adulthood. So I think you'll agree that those are both numerical. They're both quantitative pieces of information. Let's say numerical and numerical. And finally, we're asked for each one if numerical is it discrete or continuous. So the first one, the length of the dog's teeth is continuous because you can always measure length on a finer scale. Whereas Number of months is just something that you count. So it could be like 8, 9, 12. So those are counting numbers. So we're going to say here this is discrete. Yeah, so that is question one. So question two tells us that we have a microbiology course with 100 students who are writing an exam out of 60 points, and the average score is 40 out of 60 with a standard deviation of 5 points. And we're asked, what can you say about the number of students who score between 30 out of 60 and 50 out of 60? So, so this is should be reminiscent for you of the problems that you saw before the midterm, like early on in the course, before you learned about the Z table. So the only way to answer these is if they're nice cooked up numbers that are exactly like a whole number of standard deviations away from the mean. So here the average is think of as a synonym for mean. Like whenever you see that word average, it's talking about the mean. And we've got S is 5. And you can basically just see that, okay, if you're going distances of 5 away from 40, okay, that here you've got, uh, with me, you've got Z scores basically are going to be 1, 2, -1, -2. So 30 is 2 standard deviations less than the mean, and 50 is 2 standard deviations greater than the mean. You could also just do that by looking at the Z scores. So for example, 30 minus 40 over 5 is -2. And likewise, if you did 50 minus 40 over 5, you get +2. So in this case, we are exactly 2 standard deviations from the mean. So scores between 30 and 50 are 2 standard deviations away from the mean. So when we did Chebyshev's rule, we often just use the letter K to denote that number of standard deviations. And we're not told anything that this is a symmetric mound-shaped distribution. We don't know it's normal, so we can't use the empirical rule with the information we're given. So we appeal to Chebyshev. So 1 over 1 minus k squared is at least how many, at least what proportion of the students is going to be within 2 standard deviations of the mean. So that's 1 minus 1 over 2 squared is 1 minus a quarter is 3/4. So that tells us that at least 3/4, and in total there were 100 students. So I said that back at the beginning of the question. So 3/4 of 100 is 75 students scored between 30 and 50 points. Okay. Oh, and that is also just emphasize that's at least. So question 3 gives us a list of data and then says calculate the Pearson coefficient, and then is the data positively skewed, negatively skewed, or symmetric? So this is a nice straightforward computational one. Um, Basically just kind of put stuff in formulas. So so the formula we want here is going to be this one. That's our Pearson coefficient formula. So P is 3x bar minus m over s. So P equals 3. So x bar, of course, is the sample mean. So we've got to compute that. We also have to compute the median and the standard deviation. So x bar is going to be 52 plus 59 plus 61 plus 68 plus 77 plus 83 plus 83 plus 86 plus 87 plus 87 plus 92 plus 99 all over. There are 12 data points. So that's going to give us 934 over 12. So you need your calculator for that probably. And that's approximately 77.833. Okay. Next thing is calculating the standard deviation. So that one's a bit more tedious to work out. The formulas we've got are here. So we've got 2 different equivalent formulas for the variance. And then the standard deviation, of course, is just the square root of the variance. So let's use this one. I'm just going to follow what I've got in the solutions. You can use the other one, whichever one you prefer. So that's going to give us s squared, write it down again. So the sum of x squared minus the sum of each x all squared over n all over n minus 1. So that's just from the formula sheet. So there is a difference here. The sum of x squared means we add up x squared for each number in the set, whereas the sum of x all squared means we add up all the numbers and then square the answer. So let's do that. So we've got, oh, so this is going to be a pain, but okay. Here we go. So we've got 52 squared plus 59 squared, 61 squared plus 68 squared, 77 squared plus 83 squared plus 83 squared. So really you just do this in your calculator. You just got to be careful with what you're entering. $92 squared plus 99 squared. I'm going to fit all that on one line. Actually, this is just, I'm going to do it in separate pieces. This is just the sum of x squareds, just so that I can fit it on the line. So if I work that out, if I put that in my calculator, what's that going to give me? 75,036. And I already calculated my sum of x's up in the mean calculation. That was 934. So that means this is going to give us 75,036 minus 934 squared over 12 all over 12 minus 1 is 11. So what does that work out to? That works out to about 212.697. And that's my variance. So that means my s, take the square root of s squared. So that's going to be approximately 14.584. And so that gives me two of the things I need. And then I also need to find m, which is the median. And the data is already in ascending order. And because I have an even number of data points, there's going to be 2 points in the middle. So I've got these two, use a brighter color. I've got these two 83s in the middle. And so I have to take their mean. And the mean of those is obviously going to be 83. Okay, so whenever I have 2 points in the middle, I have to take the average of them. So m equals 83. Go back to my other color. And now I can compute p. So p is going to be 3 x bar minus m over s. So I've got 3 x bar again, 77.833 minus 83. You can see it's going to be negative here. Divide by 14.584. And that works out to, if you put that in your calculator, you're going to get about minus 1.063. And because it's negative, that means my data is negatively skewed. Yeah, so that one's not hard, just a bit time consuming, a bit tedious. So problem 4 says the average length of a certain species of lizard is 53 centimeters with a standard deviation of 7 centimeters. If the z-score of a particular lizard from this species is 1.4, what is its length? So if we look at the formula sheet, we have a couple formulas for z. So you could use either. I'm going to opt for this one because this is for the whole population of lizards of that species. So let me write this down. So z equals x minus mu over sigma. And average is meaning the mean. So the mean is 53. And we're told the standard deviation is 7. So if we're given z, we want to find the length of this particular lizard. So we know its z-score, and we know mu and sigma. So 1.4 equals x minus 53 over 7. That implies that x minus 53. So we want to solve for x. So 1.4 times 7. So what does that work out to? Works out to 9.8. So that implies that x, if we bring the 53 over to the right-hand side, get 53 plus 9.8. So that's going to be 62.8. So that is the length. And for part B, at most, what percentage of this species of lizard has length 60 centimeters or more? So in most questions are typically something you can apply Markov to. So Markov's inequality says, so given A, actually let me just say at most x bar over A are bigger than or equal to A. So if you look at the formula sheet, where's my cursor? Here we go. That is, all you're given here is x bar over A, and that is to kind of trigger in your mind that that's Markov. So here we've got x bar is 53. So we've got 53 is the mean, and A is the thing we're trying to compare against. So that's 60. So this is at most are bigger than or equal to 60. So 53 over 60 gives us about 0.8833. So at most 88.33% are greater than or equal to, or maybe I should say have length bigger than or equal to 60 centimeters. Yeah, so that is question 4. Okay, so we come to problem 5, and this is one that might take a little bit longer. So this is constructing a histogram, and then secondly, from the histogram, determining if the data is positively skewed, negatively skewed, or symmetric. So constructing the histogram, something you might want to bring a ruler for that if you want it to look neat and tidy. But here we've got data points from 1 to 12. And we're asked to display the data in a table that has 4 class intervals. So we want 4 intervals of equal width for histogram. So from that, you can see that 12 minus 1 gives you a distance. So the distance between the largest and the smallest is going to be 11, which is not nicely divisible by 4. So instead, what we'll do is we'll extend our table out to go all the way to 13. That way we include each of the data points and we get a distance that's evenly divisible by 4. So that means extend, so let me write that down, extend to 13, and then we get widths of the intervals are going to be then 12 over 4 equals 3. Okay, so let's make the table. So based on that, I think I want it to be black. So I'm just messing around with my stylus here to get the right appearance I want for it. So I'll have one, so I want 4 intervals. And we're told to include the class frequencies, relative class frequencies, and class percentages. So let me write that down. So we've got interval, we've got frequency, relative frequency, and percentage. And here we have 12 numbers. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 10 numbers. Write that down. So the class intervals, like I said, we're going to go from the smallest one. We'll start at 1 and then extend up to 13. So this is a key point here. I'm using what are called half open intervals. Oops, the wrong number. Because, sorry, 1 to 4, because it has a width of 3. Because I want to include all the data points, but not double count any points. So I have to have like these intervals give me mutually exclusive um, sets that partition the whole set from 1 to 13. That way, like I said, I include each number, but no number twice. So those are my intervals. And let me just write what that means briefly. So this is kind of review. But the interval from A to B means basically x such that a is less than or equal to x less than b. So it includes the left boundary of that interval, the one with the square bracket, and it excludes the one with the round bracket. Okay, so now we just count from our list. So we've got numbers between 1 and 4. There are quite a few, but we don't. So let me do that again. Make that tidier. So we don't include 4. They're just bigger than or equal to 1, but less than 4. So we've got 6. And then the relative frequency, because we have 10 in total, is 6 divided by 10 is going to be 0.6. And then how many are between 4 and 7? Just 1. How many are between 7 and 10? Just 2. And then between 10 and 13, just 1. So now we've got 1, 2, 1. And then dividing by 10, we get 0.1, 0.2, 0.1. So setting up the table is really important because otherwise your bars will be wrong on your histogram. So I noticed on the midterm that a lot of students didn't use these half-open intervals. Sometimes they were just writing numbers without using interval notation. So the interval notation really makes it crystal clear what numbers are included in that range and what ones are excluded. So in percent is just expressing this in terms of a percentage. Okay, so now we can make the histogram. So one big thing is you don't want to lose points for just not labeling it. So be sure to label and give it a title. So it doesn't have to look perfect or anything. I just want it to go. So this is a relative frequency histogram. So I wanted to go from 0 to 1. So let me highlight that. Yeah, there it is. Construct a relative frequency histogram. So relative, like I said, that means the proportion out of 1. So this is a relative. So this is my title. For the data. And here, this wasn't applied to any particular application. So we were just given numbers. So we'll just call it data. And here we'll call this relative frequency for the y-axis. And now we have to go from 1 to 13. 4, 6, 7, 8, 9, 10, 11, 12, 13. And I didn't give myself a lot of vertical room here, so I'm just going to make this 0.2, 0.4, 0.6, 0.8, and 1. And now we just plot the heights of the bars. So that's the relative frequencies. So the tallest one, as you can see, is from 1 to 4. And that gets 0.6. So like I said, you're going to want to maybe bring a ruler, unless you're just good at drawing straight lines. Then we got another one that is just 0.1 from 4 to 7. And then we've got a 0.2 from 7 to 10. And we've got a 0.1 from 13. And then if you want to make it, I don't know, look fancy or pretty, you can shade them as you see fit. Stylus is too thick for that. There we go. Okay, and part B says to determine if it's positively skewed or negatively skewed or symmetric. So actually, yeah, that's the phrasing. So here you can see that more of the data is on the left. So there are extreme points here in the right tail that are going to inflate the mean. So that means that this is positively skewed because of that long right tail and where most of the data is on the left part. So uh, the that'll cause the mean to be bigger than the median with these extreme measurements over in the right tail. Okay, so that is problem 5. Okay, so question 6 gives us a box plot or a box and whisker plot, and we're asked to identify the median, upper quartile, lower quartile, interquartile range, maximum and minimum, And then is the data positively skewed, negatively skewed, or symmetric? So just looking at the plot, we've got median is going to be the bar in the middle of the box. So that's going to be right here. So that's 8.5. The upper quartile is going to be what's sometimes called the upper hinge. So like the top part of the box where it ends is going to be 9. And then the lower quartile is the lower hinge. So that's going to be right there at 6. What else? The interquartile range is going to be QU minus QL. It's going to be 9 minus 6 is 3. Maximum is going to be 10. So in this case, there are no outliers, like there's no asterisk symbols and no circle symbols. So the most extreme measurements are just going to be at the top and bottom of where the whiskers end. So that's going to be 10 and 2 for the min. Part B, is it positively, negatively, or symmetric? So based on this, I'm going to say it's leftward or negatively skewed. And the reasons are as follows. So, so there are several things that would give evidence to that. So the leftward or negatively skewed would mean that the tail is longer in the left, that there's more extreme measurements on the left. So first thing is that the box is centered in the upper part of the range. So more of the data is in the upper part of the range. And of the data points in the box, half of them, sort of messy, sorry. Half are between M, which is 8.5, and my upper quartile, which is 9. Okay, so again, more of the data seems to be in the upper part of the range. So based on that, data is clustering in the upper part. And that means there's going to be more extreme values on the left because it's not symmetric. So a peak is to the right. With a longer tail on the left. And so that means it's leftward or negatively skewed. Okay, so that is analyzing a box and whisker plot. So question 7 says a group of 10 students are running for student government. If the government is comprised of 3 people of equal standing, how many ways are there to choose 3 of the 10 for student government? So we're choosing 3 things from 10 and it's not ordered. So we have for part A, looking at an unordered arrangement. And we're trying to count the number of ways we can do that. So that's a combination. So for the first person, there are 10 choices. The second person, there are 9. For the third, there are 8. But this is counting ordered arrangements, like first, then second, then third. So we have to divide by the number of ways there are to arrange 3 things, in this case, 3 people. So we divide by 3 times 2 times 1. There's a number of ways you can permute 3 things. And what does that give us? So 720 divided by 6 is 120, I think. Yeah. So part A, we have 120 different choices of government. For B, if the government is comprised of a president, a vice president, and a secretary, how many ways are there to choose 1 student per position in the government, assuming no student can hold more than 1 position? So this is assigning positions in an ordered manner, and so we're looking at a permutation of 3 things from 10 things. So it's an ordered arrangement. And so again, there are just 10 choices for president, say, 9 for vice president, 8 for secretary. So we get 720. Yep, so that's your standard kind of combination permutation question. So question 8 is another counting question. So here we have, there are 4 different trails to the top of a mountain. And how many different ways can Michelle hike up and then down the mountain if, so for part A, she must take the same trail both ways. So if you think, okay, there's 4 trails and she has to take the same trail both ways. So for the way up, she has 4 choices. It's going up, 4 choices. But then she has to take the same trail coming down that she took coming up. So that means that on the way down, there's only 1 choice. She has to take the same trail both ways. So that means we have 4 times 1 equals 4 choices. For part B, she can, but doesn't have to take the same trail both ways. So going up, there's still 4 choices. Going down, she can take the same trail, but she doesn't have to. So she could take any of the other trails as well. So she has 4 choices going down. Okay, so that means in total by the multiplicative principle for counting, there are 16 possible choices. And then part C, she doesn't want to take the same trail both ways. So going up, there's still 4 choices. Nothing restricting her choices going up. But going down, there is something restricting her choices. She doesn't want to take the same trail. So that means there's 3 remaining trails that are open to her. So going down, she's got 3 choices. So again, by the multiplication principle for counting, we've got 4 times 3 choices. So that's going to be 12. And for part B, I should have said, okay, 4 times 4, that's 16. Yeah, so that one in the past has kind of thrown students for a loop, but it is just a straightforward counting question. So yeah, that's question 8. Problem 9, you have a bag of 3 red marbles, 6 blue marbles, and 1 yellow marble. If you select 1 marble from the bag and it isn't blue, what's the probability that the marble is red? Okay, so this is one you can do 2 different ways. So it's a conditional probability problem. So one method is to just notice that in total there are 10 marbles and 4 of them are not blue. So out of the 4 non-blue marbles, 3 of them are red. So you have 4 equally likely outcomes, and this event of being red contains 3 of them. So that would mean the probability of, I'll say red given not blue. So use the symbol blue complement. So probability of red given not blue will be 3/4 or 0.75. Another method is to use your conditional probability formula. So here we see we've got this formula for P of A given B. It's P of A intersect B divided by P of B. So we can say, okay, P red given not blue, probability of red intersect blue complement divided by a probability of blue complement. So the ones that are red and not blue are just the number that are red, which is going to be 3. So we've got 3/10. Probability being red. Probability being not blue. So there's 6 blue marbles, so 4 of them are not blue. So we've got 4 out of 10 as a probability of not blue. And then this simplifies to just 3/4. So we get the same thing. That's just using the conditional probability formula. Yeah, so that's our conditional probability problem. So problem 10 says we have 11 equally likely outcomes, E1 up to E11. Consider these two events A and B. Are they mutually exclusive and are they independent? So for part A, about mutually exclusive, you just look at the intersection and see is it empty or not. So here A intersect B. So if you look at them, you can see that E10 is common to both. So they have a non-empty intersection, and so that means they're not mutually exclusive. For part B, B is a little bit more subtle. Um, so you may remember that one way that you can define or check independence is this property that the probability of the intersection is the product of the probabilities. So that's derived from the conditional probability formula. So in this case, we have equally likely outcomes. And there are 11 of them. So that means that each has probability 1/11th. And if we look at P of A intersect B, that is just P of this E11 event, which is going to be 1/11th, because it just has one thing in it. On the other hand, if we look at P of A, that's got 4 equally likely outcomes in it. So that's going to have probability 4/11ths. Probability of B, same thing, it's going to be 4/11ths. And so that means P of A, P of B is going to be 4 times 4 over 11 times 11, 16 over 121, which is not 1/11th. So this property of P of A intersect B equal P of A times P of B is violated. So that means they're not independent. Okay, so that's how you do question 11. So the last one I did was actually question 10. I think all the 11s in the question got my mind confused. This one's question 11. So a Warren machine is known to produce 10% defective components. What is the probability that exactly 2 out of 3 components are defective? So what that means is if you took 3 components, what's the probability of exactly having 2 of them defective? So one of the key things with this type of question is recognizing that it's a binomial variable. So we've got a series of trials, 3 trials. Uh, Either it will pass or fail the trial. So it'll have the property or it won't have the property. And for each trial, it has the same probability of having that property. So here the probability is 10%. So p equals 0.1. And that means the probability of not having that property is 0.9. And we want p of 2. from n equals 3. 3 trials. So we're counting how many have this property. So that's a binomial. And we have a formula for binomial probabilities. So that is right here. So we'll apply that. So P of x equals n choose x, P to the x, Q to the n minus x. So P of 2 is 3 choose 2, 0.1 to the 2, 0.9 to the 3 minus 2. And you can work that out in a calculator. So in a calculator, this would be probably written as, actually, the button would be NCR. But you can also say, okay, I want to calculate that and show my work, which is a good idea as well. So here we've got 3 times 2 times 1 is consistent notation, divided by the number of ways that you can arrange two things. Is going to be 2. So that's going to be times 0.1 square, 0.9 to the 1. That should work out to about 0.027. So if you recognize it's a binomial question, that one should be a pretty quick one to answer. So question 12 is that we have a discrete random variable x that only assumes the values 1, 2, and 3. And we have this function p of x that involves a constant c. And we're asked to determine the value or values of c so that p of x can be the probability distribution of x. So one of the conditions, so the key to solving this problem is partly just recognizing what to do. So with this type of problem, the thing that has to be true is that the sum of the probabilities over the different values that x can assume has to be 1. So that puts a constraint. So we need the sum of the p of x's to equal 1 for this to be a probability distribution. So let's work out what that means in terms of this formula for p of x, and that will put a constraint on what c can be. So here we have p of 1 plus p of 2 plus p of 3 equals 1. And those are the only values that x can assume, so that keeps it pretty simple. And then in terms of the formula, that means that c times 1 squared plus 1 plus c times 2 squared plus 2 plus c times 3 squared plus 3 equals 1. And that means that if we simplify that, 1 squared plus 1 is 2. 2 squared plus 2 is 4 plus 2 is 6. And 3 squared plus 3 is 9 plus 3 is 12. So then if we factor out C, so my throat just got scratchy. Yeah, so we factor out C. Sorry. We get that C has to be 1/20th. So really the problem just boils down to recognizing that that's the appropriate constraint right there that determines what C can be. Okay, so once you know that, it's pretty straightforward. So problem 13, a bus is scheduled to stop at a certain stop every half hour on the hour and on the half hour. At the end of the day, the buses are still stopping every 30 minutes, but because of delays, they're never early and likely to be late. The director of the bus line claims that the length of the time it's late is uniformly distributed. Highlight that. And that the maximum time it will be late is 20 minutes. And then we're asked what's the expected number of minutes a bus will be late. So the expected number is really asking for the expected value. So I think that what makes this problem maybe tricky is the wording that you have to remember what expected value is. And so E of X is the mean. And we have a uniform distribution with X being distributed between 0 and 20. So you might remember that the upper and lower bounds that X assume in a uniform variable, uniform random variable, are denoted C and D. And we just want the mean or expected value for that distribution. So from our formula sheet, we see that the uniform variable has mean C plus D over 2. So mu equals just the average of those two values. So in this case, it's going to be 0 plus 20 over 20. Sorry, over 2. What am I doing? I'm tired. Okay. 10. All right. So yeah, so that means that the expected number of minutes that the bus will be late is 10. Okay, so that is problem 13. Okay, so problem 14. So here, this one is really about being able to find a percentile. So we've got a college entrance exam. and that has scores that are normally distributed with mean of 550 and standard deviation of 100. And a certain prestigious university is only going to take people that score higher than 90% of the students, so at or above the 90th percentile. So find the minimum score that an applicant must receive in order to get consideration for admission. So basically we want to find that 90th percentile. So let's let X star be, how do I want to say, be the 90th percentile. And that's just like a word or phrase to express that I want P of X less than or equal to X star equal to 0.9. So sometimes that's also called the 0.9 quantile. And because it's a approximately normal distribution, we can use the Z score. So we have, population approximately normal. Can use Z score. So that gives us access to the table and allows us to figure out what this percentile is. So the Z score is going to be of X star. It's going to be X star minus mu over sigma, which is going to be, the mean was 550 and the standard deviation is 100. And so let's figure out, in terms of the Z score, what would that be from the table? So first, find Z, let's call it Z star, such that probability. So we'll do things in terms of a variable for which we have a table, and then we can from that figure out what the corresponding raw score should be. Okay. So remember, you can go between the given kind of raw score and the Z score, which is the standardized normal distribution score. So where's my Z table? So when do we have the probability is, less than 0.9? So we have to figure out like what Z is going to have area 0.9 here on the left tail. And so we look for, inside the table, we look for an area that's closest to 0.9, and it's going to be right here at this 0.997. So that corresponds to 1.28. So we've got from the table, Z star 1.28. And then we just figure out from that what should X star be. So Z star equals X star minus 550 over 100. And this Z star we just found was 1.28. So that means that X star minus 550 equals 128. Oops, that's supposed to be a star. So X star equals 550 plus 128. So that's going to be 678. And so therefore, that's basically um, demarcating where the boundary of people getting less than or equal to 90 and people getting bigger than 90 is going to be. So our answer is 678 is the score. That's the minimum score that you need to get to be considered for entrance into this university. Problem 15 asks us to find the sampling distribution of the sample median M, where we're taking samples of 3 from this given discrete probability distribution. And then we're asked to determine if M is a biased estimator for mu, the mean, and then finally to find the standard error for M. So first, probably part A is the longest. So what we have to do here is make a table of all the different samples of size 3, their probabilities, and the medians of those samples. So that's because in this case, we're being asked to do the sampling distribution for the sample median and 3 measurements. So let's do that. Let's see, okay, so we make a table, samples, 2, 3, 4, it's a bit longer. So this type of problem is a bit long, so you want to budget your time. So if you feel it's going to take you a really long time, if there's one like this on the exam, then maybe leave it for the end if you know it's going to take you a long time. But samples, uh, probabilities, and median. So samples of size 3. So X can assume 2 values. It can assume 1 or 2. And so that means we're going to have a total of 2 times 2 times 2 is 8 different samples. So I'm just listing them all. So those are all the ones that start with 1. I'm going to do the ones that start with 2. Okay, so those are all the possible samples. And we also have a distribution for X. So, so here having 1, 1, 1, that's going to occur with probability 2/3 times 2/3 times 2/3. is going to be 8 over 27. And 112 is going to be 2/3. So you have to just keep going like this. So 2 happens with probability 1/3. So we get 4 over 27. And so these events are independent. So I'm using the multiplicative principle for independent events and taking the product to find the probabilities. So here I've got 1, 2, 1. So I've got 2/3, 1/3, 2/3 equals 4 over 27. So maybe just to save time, I'm going to do it mentally. So I've got 2/3, a third, a third. So that's going to give me 2 over 27. Again, this one's going to give me 4 over 27. 2 over 27. 2 over 27. And 1 over 27. I just mentally check that I did that. Okay, so the median, this one you do have to be a little careful because the way the samples are arranged is not in increasing order. So you have to mentally put those numbers in ascending order when you take the median. So here 1, 1, here 1, 1, 2. So in increasing order, the middle number will still be 1, 2, 1, 2, 2, 2. Okay, so that's the first step. And now we can compute probabilities. So M can assume only 2 values, 1 and 2. So P of M equals 1. Oops. P of M equals 1. So we have to add up the different ways, the probabilities for the different ways that M could be 1. So here we've got in the first, second, third, and fifth rows are all M equals 1. So there we have adding up the probabilities of the different outcomes. So this is by one of the axioms of, I think, the additive rule for probability. So we got 8 over 27 plus 4 over 27 plus 4 over 27 plus 4 over 27 is going to give me 20 over 27. I'll have a common denominator. And then P of M equals 2. So again, for these are separate outcomes. So I add up their probabilities. So I've got the fourth and the sixth, seventh, and eighth lines all have M equals 2. So those correspond to in the middle column, I have 2 over 27 plus 2 over 27 plus 2 over 27 plus 1 over 27. So it's going to give me 7 over 27. So that means that the sampling distribution, to answer part A, sampling distribution of M, we can make a little table. So M can assume values 1 and 2. And the probabilities with which they occur are 20 over 27 and 7 over 27. And for that to be a probability distribution, those need to add up to 1, which they do. If they didn't, then you might have made a mistake. You must have made a mistake in your past in this table. So so that's one way you can just quickly check, are things lining up right? Part B says, is M a biased estimator from U? Sorry, so this was part A. Part B. is M biased estimator or mu. So for that, we're going to calculate the expected value of M and see if that is equal to the mean. So E of M is M P of M added up. So that comes from, for discrete variables, we can calculate their mean or expected value from this formula. So that's right there. That's what I'm using, but I'm applying this to M because I now have this variable M. It comes from taking the means of samples of size 3. And so here, what do I got? That's going to be 1 times 20 over 27 plus 2, 7 over 27. And that's going to work out to 34 over 27. On the other hand, we have the distribution already for x. That's up in the question. And so let's do the same thing for that. So mu equals E of x equals sum x p of x. That's going to be 1 times 2/3 plus 2 times 1/3. So again, that comes from the table in the question, and that works out to 4/3. And these are not equal. So therefore, M is a biased estimator for the mean. And lastly, part C is calculating the standard error of M. So that's the standard deviation of this variable. And so again, from the formula sheet, we have for a discrete random variable, we have a formula for the variance. So we have 2 formulas. So you could use either of these. And then you just take the square root to get the standard deviation. So the standard error is the standard deviation. So this is the new variable that you get with the sampling distribution. You take all the samples of size 3, and then you take their means, and that makes a new, sorry, you take their median, and that creates a new variable. And then when you take the standard deviation of that, that gives you what's called the standard error. So let's compute that from the formula. So first we do the variance. So this is, again, like a long time consuming question, but we can manage. And so that, like I said, just came from that formula on the formula sheet, but applied to M. So this formula, whoops, here. And this works out to, so M can assume 2 values, so the sum is not too long. And we saw that the E of M, the mean for M, is 34 over 27. The probability for m equals 1 from our little table is 20 over 27. Oops, I forgot the square. And then we've got 2 minus 34 over 27 squared times p of 2 is 7 over 27. And that all works out to, what do we have? If you do some simplifying, or if you just plug that in your calculator, that should work out to 140 over 729. And so lastly, we take the square root, and that gives us about 0.438. So not too bad. Yeah, that's still one of the longer questions though. And yeah, that's how you would answer this question. Problem 16. This is a sampling error question. So we're told that the manufacturer of NFL footballs wants to inflate footballs to this pressure of 13.5. And just due to uncontrollable things and random phenomena, the actual inflations are going to be between 13.3 and 13.7. but they want to estimate the mean inflation to within 0.025 pounds with a 99% confidence interval. And then we're asked what sample size is needed to do that. So you might remember that the sampling error is it's basically a measure of the error that's incurred when you use a confidence interval, and that's determined by the radius of the interval. So basically half the diameter of that interval. That's the error that comes with the interval, and that's called the sampling error. So here we're told that we want to estimate the mean with a confidence interval within 0.025. So that's the sampling error that we're willing to tolerate. And we're asked how large do we need to make the sample in order to ensure that that's the sampling error. And there is a formula. So let me just get the formula sheet right here. So this is for means, and then this one's for proportions. So we'll use this one because we're estimating the mean. And let me write that down. Z alpha over 2 sigma, or sorry, squared, sigma squared over the sampling error squared. And so we know we're given SE is 0.025. We want 99% confidence interval. So that means that we have alpha over 2 is going to be 0.005. And Z alpha over 2, that is one of the quantities that we need to determine. We can find that from the Z table. 0.005. And how do we find that? So that's going to have an area of 0.005 in the upper tail. So that means that we have probability of Z less than that critical value is going to be 1 minus 0.005 is 0.995. So from the table, we go, where's my cursor? There we go. So this is my Z table. And so I need 0.995 in the left tail. And then so we look and find 0.995 in the table. So that is right between these two. Exactly halfway between them. So because it's exactly halfway between them, I'm going to take their average. So this is 2.57 and 2.58. And so I'm going to get 2.575. So that's from the Z table. And now I have the SE, I have the Z alpha over 2, but I don't have sigma. So the variance, how can I find that? So the trick is that because it's not given, but we're given the range, you can estimate sigma with the range divided by 4. So that actually follows from Chebyshev's rule. Sigma is approximately R over 4. And so the question tells us that the minimum is 13.3 and the maximum is 13.7. So R equals 13.7 minus 13.3, 0.4. R over 4 is going to be 0.1. So that is our approximation of sigma. So therefore, the sampling size we need is going to be was it Z alpha over 2 squared times sigma squared all over SE squared and this was 0.025, and that works out to about 106.09. So for sampling size, to ensure a certain sampling error, you always round up. So we get n equals 107 is the sample size you need. To ensure the pressure is within so I should say the mean pressure is within 0.025 of the true value. Yeah, so that's question 16. So problem 17, basically we've got a telephone survey of 1,000 American adults, and of those, 73% believe that Starbucks coffee is overpriced, and we want to use this to form a 95% confidence interval about the true proportion of Americans who believe that Starbucks coffee is overpriced. So it is a confidence interval question, 95% confidence interval, and it's about proportion. So let P equal proportion of all Americans who believe, I'll just say overpriced. And we have a sample of 1,000. And so those give us a sample proportion of P hat is 0.73. And so the sample proportion of those who don't believe is overpriced is going to be Q hat. It's 1 minus P hat is 0.27. So for confidence interval, we do have all the formulas that you need on the formula sheet. So this is the formula you're going to want. So write that down. P hat plus or minus Z alpha over 2 square root P hat Q hat over N. And the reason why we can do that is we have to check, is this a large sample situation? So we're using a Z statistic here. So let's just check that. So NP hat is 1,000, 0.73. So that 730 is certainly bigger than or equal to 15. And Q hat, 270, also bigger than or equal to 15. So therefore, said statistic is valid. And so we can indeed use this formula. So Z alpha over 2. So the idea is with a confidence interval, you're going to have alpha over 2 in each tail. So in this case, that's going to be 0.025. And then in this case, 95% will be in the middle. And so we look at what's the critical value that marks off that boundary in the upper tail. So it's going to have area of alpha over 2 in the upper tail. So that's going to be Z 0.025. And so we need that from a Z table. So from the table, you can find Z 0.025 is 1.96. And so we get the interval is going to be 0.73 plus or minus 1.96, 0.73, 0.27, all over 1,000. And that works out to 0.73 plus or minus 0.028. So that it gives that P has to be with 95% confidence between 0.702 and 0.758. Yeah, so that one's pretty straightforward. You just have to know what situation you're in, what formula to apply. Do check that the sample size is large, and so it's a valid test. And yeah, that's question 17. Problem 18 is a question about the average or mean aggression level in primary children. So we're told that there's a scale of 1 to 5, for 1 being not aggressive and 5 being very aggressive. And in 1980, teachers found that the students had an aggression level of 1.75. And in 2024, a study was done of 11,160 primary school children and found a mean aggression behavior score of 2.15 with a standard deviation of 1.05. Psychologists are interested in whether the aggression rating of primary school children has increased from 1980 to 2024, and were asked to conduct a test of hypothesis using the p-value approach. Alpha is 0.05, and state the conclusion reached by your hypothesis test. So we don't really have much information for the 1980 data. We only are told X bar is 1.75. And so there's no sample size, no standard deviation associated with that number. And in 2024, a study was done where we had n equals 11,160. X bar is 2.15. And also we're given the sample standard deviation is 1.05. So because we don't really have much information about 1980, we can't really do a two population comparison. But what we can do to set up a hypothesis test is we could just compare, so let mu be the mean. We could compare the aggression level in 2024 to just the number 1.75. So if we let mu just denote the true mean level of aggression in 2024, we can test. So status quo, until proven otherwise, we can just assume it's the same as it was in 1980. And we'll see if this study gives enough evidence to show that, in fact, it's bigger than what it was in 1980. That'll be our research hypothesis. Okay, so test of hypothesis, if we look at our formulas, here we've got the Z statistic is our test statistic. And so Z, I sometimes write ZC for the test statistic. And sometimes I also use a zero subscript to note that this is the hypothesized mean that we're comparing against. So we're looking at the Z score. If we looked at the distribution with mu naught there, this is the sampling distribution of the mean. On that distribution, what would be the Z score of the measured test statistic? So here we've got 2.15. So we want to know what's the Z score of that. So 2.15 minus the hypothesized mean was 1.75. It's what we compare against. So we're basically in inferential statistics trying to see how unlikely is this measurement. And then S was 1.05 over root. I just realized I'm forgetting to tell you something. So before we do this, so is this Z statistic justified? I just kind of jumped in and said, oh, well, we can use a Z statistic, but of course we have to know we have a large sample. So we have n equals way bigger than 30. So CLT means it's Z statistic. So we can use that that formula that I pointed out there. Kind of jump the gun on that, but you do want to verify that for sure. Okay, so back to this test statistic, that is going to work out to about 40.244. Okay, so that's a really large Z value. So the table only goes up to about 3.5. And then you can see that the area starts to get to like 0.9999 under the curve. So, and that's in the left tail. So in the right tail, your area is getting smaller and smaller. So for such a large Z value, your p-value is going to be astronomically small. It's basically going to be 0. 0, of course, is less than our significance level. And so we reject H naught at this level of significance, and then state our conclusion. So data supports the idea that the mean aggression level increased between 1980 and 2024. So yeah, so that is question 18. So problem 19 is about hammer-headed sharks. So it's known that they're normally distributed with a mean length of 21 feet. However, one marine biologist believes that the ones off the coast of Bermuda are of a different size because of their different feeding habits. And to test this claim, they captured three adult hammerhead sharks, and they only got three because, of course, they're dangerous and expensive to capture. And so the lengths of those three were 24, 22, and 20. So it says conduct a test of hypothesis using the rejection region approach at zero point 0.1 significance level, and furthermore state the conclusion reached by your test of hypothesis. So basically, this marine biologist's claim is that the mean length is different from what it's known to be. So it's known to be 21, and it doesn't say bigger than or less than. So that's another thing, just of a different size. So that should tell you that the alternative hypothesis is just not equals. So it's a two-tailed test. Also, we've got n equal 3 is way less than 30. And so we have to use the t-statistic. So if we look here, our t-statistic is x bar minus mu over s over root n, and the degrees of freedom associated with that are n minus 1. So we've got, let me write that down. I should also say that we are in the one case where we can use the t-statistic. So that is the case where sigma is unknown. So we have small sample, sigma is unknown, and the population is known to be approximately normal. So that's like the one and only one case where the t-statistic is appropriate. So here we've got TC. Sometimes I see for the computed or the test value, it is x bar minus mu. And I also sometimes write the mu naught to indicate that's the hypothesized mean over s over root n and minus 1 degrees of freedom. So what do we have? We only know the lengths. So the sample has lengths 20, 22, 24. So they don't give us the mean, the sample mean and the sample standard deviation, but they're very easy to compute. So let's do that. So x bar, I can see just by looking at it, x bar is 22. Let's do it. 22 plus 24 over 3 equals 22. And s squared, the variance, is going to be 20 minus the mean squared plus 22 minus the mean squared plus 24 minus the mean squared over n minus 1 equals 2 squared plus 0 squared plus 2 squared over 3 minus 1 is going to be 8/3. No, 8 over 2, sorry. 8 over 2 is 4. So therefore, S, the standard deviation, is square root of 4 is 2. So we calculated our descriptive statistics, and so that means we are able to use the formula now. So TC is x bar is 22 hypothesize means 21 all over 2 over root 3 is going to be root 3 over 2 is going to be 0.866. And we also need to figure out what's the rejection region. So we're told to use the rejection region approach at alpha is 0.1. So rejection region alpha equals 0.1. So it's a two-tailed test. So we have to consider what's T alpha over 2 is T 0.05 with 2 degrees of freedom. So from the table, from the T table, that will give you 2.92. And so the rejection region for two-tailed is going to be T absolute value bigger than T alpha over 2, i.e. any T whose absolute value is bigger than 2.92. So basically that means if your T value is here's 2.92, here's minus 2.92. If it's further away from 0 than 2.92, then your absolute value is bigger than 2.92. Our statistic, though, was 0.866. So TC is right about here. So TC is not in the rejection region. It's not bigger than 2.92. So we cannot reject H naught. And so that means our conclusion is that data doesn't support the claim that mean shark length for the hammer-headed sharks is different from 21. So yeah, so that's a T statistic type question, and yeah. So question 20 is about fear of negative evaluation scores for 11 students who suffer from anxiety and 14 who do not suffer from anxiety. And so the fear of negative evaluation is some score that they have um, measuring their fear of negative evaluation, and we're asked to construct a 97% confidence interval for the differences in FNE scores between the students with and without anxiety. And we're told that the FNE scores are normally distributed. The variance is the same for both populations. So here we've got N1 is 11, which is small, and 2 is 14, also small, less than 30. The variances are equal but unknown. Unknown variances and small samples, and both populations are normally distributed. Oops. So all those things tell me that I need to use t-statistic. So if we look at the formula sheet for two samples, so we're comparing these two populations and we want a confidence interval. So we're going to have to use this formula where this SP squared is the pooled variance. That's right here. So that's like the weighted average of the two sample variances. So let me write that down. T, and we've got confidence interval plus or minus T alpha over 2 SP squared over N1 plus 1 over N2. And alpha is 0.03, implies alpha over 2, 0.015. And then from the table, we can find that t-value is going to be, what is it going to be, 2.313. And let me also write down what the pooled variance is. Over, what is that going to be? N1 plus N2 minus 2. And the t-statistic here also I should have said is based on N1 plus N2 minus 2. So that is going to be, what is that, 23 degrees of freedom. That's how I found this t-value. And so because I'm not given in the question, unfortunately, we're not given S1 squared and S2 squared, nor are we given X1 bar or X2 bar. So that is kind of unfortunate. That means we have to do some computation. So maybe what I'll do is write, just to help me, actually, I'll call it pop 1 and pop 2. I might make some tables of the values. So the x's, and then x squared, x squared. So the x values are for the anxiety we'll say is population 1. Let's write down the numbers. So we got 21, 13, 10, 20. I don't know if this is the best way to do this. I'm just trying to come up with a way. 19, 16, 21, 24, and 13, 14. Because at the end of the day, I'm going to have to add these up to calculate the mean, and I'm also going to have to add up the squares of them to calculate the variances. So let's do the same for population 2. We've got 13, 6, 16, 13, 8, 19, 23, 18, 11, 19, 7, 10, and then 15 and 20. And then at the bottom, we can write what do these all add up to? So from a calculator, see if it's actually in the notes. So I think these should add up to 196. Is that right? So let me test it. So 21 plus 13 plus 20 plus 25 plus 19 plus 16 plus 21 plus 24 plus 13 plus 14. Yep. 196. And then the other ones I think should add up to 198. And now x squared. So this is super tedious. 441. 13 squared is 169. I think. Yeah. 100. 400. 625. 19 squared is 361. 16 squared, 256. 21 squared, oops, 441. 24 squared, 576. 169. 196. So I'll add all those up in a second. Let me do the population 2. Some of them I can find in the ones I just did. 13 squared is 169, 64, 361, 23 squared, 529, 18 squared, 324, 21, 19 squared again. Is it 19, right? Yep. 361, 49, 100, 225, 400. Okay, so now we got to tally all those up. So 441 plus 169 plus 100 plus 400 plus 625 plus 361 plus 256 plus 441 plus 576 plus 169 plus 196 equals 3734. And then what do we get for the other? 169 plus 36 plus 256 plus 169 plus 64 plus 361 plus 529 plus 324 plus 121 plus 361 plus 49 plus 100 plus 225 plus 400. 3164. Okay, all right, so now we can use our formulas for the variances. So these are on the formula sheet. So we do it for each population. Oh, sorry, I also want to do the means. All worried about the variances because they're kind of a pain in the ass to do, but these means are not too bad. So x1 bar is going to be 196 over 11, which works out to about 17.818. And then x2 bar is going to be 198 over 14, which will work out to about 14.143. The S1 squared, the variance is going to be 3734. Actually, let me write down. So there are two formulas for the variance, just like we did in an earlier problem. Divide by n minus 1 is going to be 11. So that'll work out to about 24.164. And the S2 squared is going to be 3164 minus 198 squared for 14 all over size minus 1 is going to be 13, which will work out to about 26.320. Okay, so now I can do the pooled sample variance. It's going to be 24.164 and 1 minus 1. I'll just write what that is. That's going to be 10 plus 26.320 times 13 all over n1 plus n2 minus 2 is going to be my 23 in the denominator. So that's going to work out to, oh shoot, I'm looking at the solutions and I copied something wrong. Okay, darn, sorry, this was supposed to be, too tired today. Okay, so this was actually, I was just looking at the solutions instead of putting it in a calculator, which led me astray. So this should have been 27.978. So let me correct that here. And now this should have worked out to the 26.320 number. Okay, so now we can use this formula up here to get our confidence interval. So we've got x1 bar minus x2 bar. So that's going to be 17.818 minus 14.143 plus or minus the T alpha over 2 gave us 2.313. And then we've got square root of the pooled variance (1 over 11 plus 1 over 14). So all of that will give us, at the end of the day, what is it? Get an interval from minus 1.106 to, actually, no, I'll just write it as an interval first, to 8.456 with 97% confidence. So that means that my difference of the two population means with 97% confidence is in this interval. So let me just write that. mu1 minus mu2. So this Greek letter epsilon means it belongs to, it's in that interval. Okay, so that is question 20. That's a long one. So again, if you look at that and you start doing it and you're like, oh, this is going to be a lot of calculation, then maybe leave that one for the end because it might not be worth it if it's going to take a while. Do it at the end, basically, if it's a long one like that. So the last question on the sample, question 21, is the regression question. And this one's also potentially a bit computation heavy, but there's only 5 data points, so it's not too horrendous. So we're asked to compute the coefficient correlation, are the variables correlated, and then calculate the least squares line and use to estimate the score out of 20 for a student who studies 5 hours. So it's just a straightforward thing of like hours studied versus their mark out of 20. So let's follow the formulas. So the formulas are all at the bottom of page 1. All these ones are regression formulas. So what I like to do is make a little table. So so this is basically X, hour studied, and their mark out of 20 is Y. So let's do it X, 1, 3, 4, 6, and 8. And the bottom, I'll do sum. And I'll also do the mean for X bar and Y bar. Not for the other ones, but just for those two things. But before I write Y, I'm going to write X squared. I'll write Y. Actually, maybe I'll give myself a bit more space. And Y squared, and then I'll write XY. Because when I do the formulas, the SS sum of squares for XX and XY, that's what I'm going to be using a lot. So X squared, 1, 9, 16, 36, 64. Y is 11, 16, 15, 20, and 18. We need a calculator for some of these. I think that's 256 actually. 225, 400. 18 squared is going to give me 324. And then XY is 11. 3 times 16 is 48. 4 times 15. I got to make sure I'm looking at the right values. 60. 6 times 20 is 120. 8 times 18, I don't know. 144. And now I'll sum these. So X is 1 plus 3 is 4 plus 4 is 8. 14, 22. I'm too sleep deprived today, so I don't trust my brain. Check it. Yep. And then 22 divided by 5 is going to give me 4.4. That's my X bar. And then X squared, 1 plus 9 plus 16 plus 36 plus 64, 126. Y, what do those add up to? We've got 11 plus 16 plus 15 plus 20 plus 18 is going to give me 80. So 80 divided by 5 is going to be 16. It's my Y bar. Okay, and so this is the computation part. 121 plus 256 plus 225 plus 400 plus 324 is 1326. And then XY, 11 plus 48 plus 60 plus 120 plus 144 equals 383. Okay, so I've got my X bar, my Y bar. We'll just circle those, X bar, Y bar. And so I need to compute my SSXX. That from the formula is going to be my sum of X squared minus sum of X all squared over N. So N is 5. There are 5 observations in the data, 5 points. And so having the table helps me here because I know my sum of my X squared is 126 minus the sum of X is 22, and I have to square that, 22 all squared. It's maybe we'll just write that as a separate step, 22 all squared over 5. And what's that going to work out to? That's going to work out to, should be 29.2. Do it, 126 minus 22. So you got to be careful about your order of operations here too. 22 squared over 5. So you got to use enough parentheses in your calculation. So yeah, 29.2. And then what do we have? SSYY is going to be same kind of deal. Sum of y squared minus sum of y all squared over n is going to be, sum of my y's came out to be 80. No, sorry, sum of my y squareds came out to be 1326 minus my 80 squared over n. I know n already, so I'll just leave it as 5. And that one should come out to 46. And then lastly, my SSXY, very similar looking formula. Sum of xy minus sum of x, sum of y over n. So my xy's came out to add up to 383, equal sign, minus my sum of my x's was 22 times 80 over 5, and that should work out to 31. Okay, that's the computation part, and that already took me almost 8 minutes, but let's see where are we at. Okay, R is SSXY is going to be 31. So let me just write out the formula. Um, 29.2 times 46. So that's going to give me 31 over, well, it's going to be, if you put that in a calculator, it should come out to 0.846 about. Okay, so the variables are strongly positively correlated. Because we have a positive number close to 1. Okay, so I know that's not very enlightening to watch me crunch through all that, but maybe seeing like how I set up the table is maybe helpful. And the next part though is from formulas. So our least squares line, the first thing is to find the beta 1 hat. That's our least square slope estimate. It's the SSXY over the XX. 31 over 29.2 is about 1.062. And then the beta 0 hat is our least squares intercept. So that's y bar minus beta 1 hat x bar. And that's going to be 16 minus 1.062 times 4.4. That works out to about 11.327. So that means my line, I know the slope and the intercept. It's 111.327 plus 1.062x. Okay, And then I can use that very last thing on the sample exam. I want to estimate the mark that they get if they studied for 5 hours. So estimate y at x equals 5. I just plug 5 into the least squares line equation. So y hat of 5 is going to be 11.327 plus 1.062 times 5. That's going to work out to 16.637. So that's our estimate if they studied for 5 hours, what they'd get out of 20. Yeah, so thanks very much for your time and your hard work and your studying. Um, I hope this review session is somewhat helpful. Otherwise, Ryan's is there as well. So that is, I think, on the 11th at 6 p.m. in the RBC lecture hall. All right, thank you very much and happy studying.